Hi, my name is Seyed from EDD Academy, and today I'm going to be covering Unit 7 on differential equations. First, what is a differential equation? A differential equation is an equation that relates a derivative of a function to other variables. Okay, so some examples of differential equations you may have seen are f is equal to mass times the time derivative of velocity, also known as f is equal to ma. dy dt plus f of t times y is equal to 0, very common differential equation. And this final one is from physics, bonus points if you know where it's from. Now, where are differential equations used? You want to know where the applications are. Now, differential equations are used to model almost any phenomena that involves change. Now, phenomena that involves change is very broad. It's in many different subjects. Examples are the sciences, such as physics, chemistry, astronomy, biology, or in finance, right? So, like I said, these examples are physics, chemistry, finance, astronomy, etc. There are many more fields. Change is everywhere. Now, how do we model situations with differential equations? Now, in order to model a situation with a differential equation, there are two key things to identify first. Now, first is the derivative, pretty obvious, and the function. Now, this is stated in word problems or problems in general by saying the rate of blank increases or decreases by. Now, blank is usually the function, right? So an example is the rate that the population of rabbits increases by is, and now the population of the rabbits is the function that we're looking at and we're trying to solve for potentially, and the rate of implies a derivative. In this case, it's time derivative. However, look for what the derivative is taken with respect to, but most likely it's probably going to be time. Now, the proportionality relationship between the variables is also very important. Now, obviously, if it says equals to, that's pretty self-explanatory. You'll already have like a basis to set up your equation. But there are phrases such as, let's say, dy dt is proportional to y, okay? Now, that would mean that dy dt is equal to some constant, let's call it c, times y, okay? And if it says it's equal to some constant times y, well, I mean, even easier. Now, more broadly, there may be some phrases that hint at the connection between the function, the derivative, and any other variables or constants, but proportionality or an equivalence are the most important ones. Now, here's an example. The rate that a population of rabbits grows is equal to some constant c multiplied by the population of the rabbits at that time. Model the scenario with a differential equation. Because here's some key words. The rate equal to the constant c, the population of the rabbits, and multiplied. Here it is in math language. Population, the time derivative, and c times p. Let's put it all together. We got, finally, the time derivative of the population is equal to c times p of t. Now, as you can see, the rate that the population of rabbits grows, dp dt, is equal to the constant c times the population of the rabbits. This equation encompasses all of that. Another example. The rate that the volume of a cone changes with respect to time is proportional to the height multiplied by the radius times the rate of change of the radius. Now, in this situation, there are two derivatives here, each on a different function, namely the volume of the cone and the radius. If this was on a test, they would specify which is the main function you're probably solving for, and which is a quote-unquote constant. What I mean by constant is that they would give you what r of t is equal to explicitly, or they would tell you what the derivative is, etc., etc. Now here's the answer. The volume of the cone we're going to represent with v of t. The rate of change of the volume we're going to represent with dv dt. The radius of the cone, similarly, is going to be r of t. The rate of change of the radius is going to be dr dt. Now, dv dt is proportional to h, the height, times dr dt times r of t. Normally, we'd write this as dv dt is proportional to each of these things individually, and then put it all together in this form. However, the problem explicitly tells us that it's equal to the product of these three things, so we don't need to go from that basic step to the step we're at right now. Now, since it's proportional to, there is some constant c that we have to multiply by the left-hand side to make it equivalent to. And voila, we got our constant. Here's the equation. We're done. Now, how do we verify a solution to a differential equation? We want to make sure the solution that we've gotten or that we've come up with is true. I mean, just like with algebra, you just plug it in. You plug it into the equation for where you solved it, and you just try it out. Example, dy dx is equal to some constant c. Pretty obvious, pretty standard stuff. Y is going to be some linear function. Y is going to equal to cx plus the constant of integration. Now to verify the solution, we'll plug it in where y was. D dx of this linear function is obviously going to give us the slope, and the slope is c. Therefore, this is a valid equation, and that was a valid solution. Now, we've just talked about solutions and modeling, etc. But how do we find these solutions for differential equations? All right, so here's a simple equation that we should all know how to solve. It's a linear equation. 5 is equal to 3x plus 2. What's the first step? First, we isolate x. All right, let's put all the constants on one side and all the x's on one side. In this case, easy, subtract 2. 3 is equal to 3x. Clearly, the answer is x is equal to 1. But we solve this equation by putting all the x's on one side and all the constants on another. For certain simple differential equations, your goal is to get all the quote-unquote variables or functions, for example, y, on one side, including the derivatives, and all the constants or x's on the other. Okay. Now, let's review real quick. Differentials. Given dy dx is equal to f prime of x, what is the differential form? Really easy stuff. dy is equal to f prime times dx. Okay. Now, when you're taking an integral, you usually write, integral sign, function, dx, right? However, this differential is already there, so you can just add that integral sign. So, dy is equal to f prime of x times dx. Smack that integral sign right in there. And then, carry it out. Really easy integration. Y is equal to f of x. Makes sense. Plus some constant c. I forgot to add it in. My bad. Now, here's an example. Solve the following equation for y of x. Alright, looks a little bit messy, looks a little bit difficult. It's pretty easy once you get down to it. First step, get all the x's on one side and all the y's on the other. Okay, dy dx is equal to 1 over x to the 5th, or just divide by x to the 5th there. Okay, then multiply by y minus 1 to the 4th. Okay, and now we got dy dx times y minus 1 to the 4th is equal to, we can do a little bit of simplification, 1 over x to the 3rd. Now, let's get this thing into differential form and start the integration process. Okay, so smack that integral sign onto that previous expression once we got into differential form. Pretty easy to get into differential form. Okay, now we got that expression right there. Let's carry out this integration and solve for y. Okay, pretty easy integral. You can do some simple u sub on the left-hand side and on the right-hand side. Pretty simple power rule stuff. Okay, and we end up with 1/5 of y minus 1 to the 5th is equal to minus 1 over 2 x squared plus c. Okay, so there should be a constant of integration on the left-hand side, but you can absorb it into the constant of integration on the right-hand side. Alright, so I multiply by 5 on both sides, and the reason why it's c prime is that it's not the same constant as before. It's multiplied by 5, but I just absorbed that 5 into the constant. Okay, finally we take the 5th root and add 1, and voila, we got a general solution. Now, I want to talk about initial conditions here. Okay, an initial condition is a value that the function takes at a certain point in time that is specified as the starting time. For example, at t is equal to 0, y of 0 is equal to 5. Initial conditions allow you to find the value of constants of integration to make general solutions into particular solutions. Recap, general solutions are those solutions with the constant of integration there. They'll satisfy the equation for any value of that constant, and particular solutions are once you've applied those initial conditions. For example, the general solution to dy dt is equal to 5 times y of t is equal to y of t equals e to the 5t plus c. Given that t is equal to 0 and y of 0 is equal to t, what is the particular solution satisfying these initial conditions? Okay. So we got the problem right here, and now let's solve it. So answer, we plug in t is equal to 0 and y of 0 into the general solution. Okay, so we got y of 0 is equal to e to the 5 times 0 plus c. Based on what the stuff they've given us, e is equal to e to the c. Obviously, c is equal to 1 in this case. Plug that back into the original equation, and you got your particular solution. Now, in this equation, has to satisfy the original equation, and surely it does. Now, a differential equation modeling an exponential situation follows the following formula. dy dt is equal to k constant times y. The general solution to these equations is always y of t is equal to e to the kt plus c. And on the right hand side, I used some exponent rules, and c sub e is just e to the power of c. It's still a constant of integration. Just keep it there. Alright. Now here's an example. Find the particular solution for the following differential equation given that at time t is equal to 0, y of 0 is equal to 10. Alright? So we know that the solution to this equation is of the form y of t is equal to e to the kt plus c. We could also use the other form, but I'm just going to be using this one for now. We just need to find c since k is equal to 20. Plug in t is equal to 0 and y of 0 and solve. Okay, like I said, k is equal to 20, but I mean since t is equal to 0, that wouldn't even matter in this case. Now we know that 10 is equal to e to the power of c. Take the natural log of both sides, and we get the natural log of 10 is equal to c. We plug that in, and notice how if we had actually used the second form, it would have actually been slightly easier to find the constant. Since using exponent rules, we can break that down to e to the power of ln of 10 times e to the 20t. Alright, that simplifies down to 10 times e to the 20t. Alright, thanks for watching this short video from EDD Academy. Be on the lookout for our future videos. Thanks for watching. See you guys later.